Ways of expressing concentrations of solutions. There are quite a few ways of expressing the concentration of a solution. The fundamental idea is that we are expressing a ratio relating the amount of solute to the amount of solution or the amount of solvent. How we express those amounts gives us the different units of concentration. Let's walk through the definitions of a number of concentration units. Mass percentage. The percent by mass, or mass percent, of a solute is the mass of the solute divided by the mass of the solution, multiplied by 100 to convert to percent. To calculate the mass percent, we need, obviously, the mass of solute and either the masses of all the other components of the solution or the mass of the solution itself. Note that the ratio, mass of the component over mass of the solution, is multiplied by 100. The percent means per 100. This could be called parts per hundred, or pph. For example, if a solute had a mass percent of 8.5%, that means there are 8.5 grams of solute per 100 grams of the solution, 8.5 parts per hundred. This idea has a direct application when talking about the related measures that are commonly used when talking about pollution or contamination. Parts per million has the same ratio of mass of the solute divided by mass of the solution, but is multiplied by 1 million, 10 to the sixth, instead of 100. For parts per billion, we take the same ratio, mass of solute over mass of solution, and multiply by 1 billion, 10 to the ninth. In recent years, improved testing technology has allowed us to begin to talk about parts per trillion as well, where we would multiply by 1 trillion, or 10 to the 12th. These last three units are used when there are very small amounts of the solute present. Volume percentage. Volume percentage is the volume of the solute over the total volume of the solution times 100 to convert to percent. Volume percent is most commonly used for solutions of liquids in liquids, like wines and other alcoholic solutions. To determine the volume percent, we need to know the volume of the solute and the volume of the solution. We cannot simply add the volumes of the components of the solution, since the volumes are often not additive. The volume percent is not constant, since the volume of a liquid changes with temperature, so it must be defined at a particular temperature. This lack of a constant value means that it is seldom used when high precision is desired. Mole fraction, X. Mole fraction looks at the relative number of particles, moles of solute over total moles in the solution. It is a number between 0 and 1. The higher the number, the more of the substance is present. The sum of all the mole fractions of all the components is 1. We can find the mole fraction if we know what the components of the solution are and what the mass of each of the components of the solution is. It is not uncommon to want to know the mole fraction of the solvent rather than the mole fraction of the solute. So please be aware of what it is exactly that you're trying to find the mole fraction of. Molarity, capital M. We have already been exposed to the unit molarity, moles of solute per liter of solution. It is the most commonly used concentration unit in chemistry, and is a quantity that also varies with temperature, since the volume of the solution will change with temperature. We can get the molarity from the mass of the solute, if we know what the solute is, and the volume of the solution. Again, we must know the solution volume, since volumes are not necessarily additive. Molality, Molality, symbol lowercase m, is the moles of the solute divided by the kilograms of the solvent. Molality is often used when we have two solids mixed to make a solution. Since moles and mass are not affected by temperature, the molality is constant. Molality is the unit used when we are doing calculations of two of the four colligative properties. To calculate molality, we need the mass of the solute and the mass of the solvent. This diagram shows the connections among the different concentration units and how we might calculate some particular unit from information we have been given. Note that each concentration unit is connected to the information in the center by a particular color. For example, suppose we wanted to find the molarity, capital M, of a solution. The diagram shows, with the color pink, that we need to have the moles of the solute and the volume of the solution. But suppose I am not given those quantities. I might have been given the mass of the solute and the mass of the solvent, for example. The diagram shows that you can get the moles of the solute from the mass by using the molar mass of the solute, and that adding the masses will give us the mass of the solution, from which we can get the volume if we know the density of the solution. What the diagram emphasizes is that from relatively little information, seemingly not directly connected to the quantity we are trying to calculate, we can actually calculate most of these concentration units. From 4 pieces of information for a solution with one solute, for example, we can actually calculate all 6 different concentration units. Specifically, if we are given the mass of the solute, the mass of the solvent, the density of the solute, and the density of the solution, we can calculate all 6 values. Assuming, of course, we know the formulas of the solute and solvent so we can determine their molar masses.